Good afternoon, and today's topic is wave function. Wave function means it is a representation of electron motion in space, and it is denoted by a Greek letter psi. And this wave function varies with both time dependent function as well as the position dependent variation, and it is called as total wave function, and given by the expression psi, which is equal to a into e raised to I kx minus omega t. It is nothing but it is a representation of electron motion. For example, in straight line we are denoting it by some expression, that is y is equal to mx plus c. The same thing, the electron motion is also represented by psi, which is equal to a into e raised to I kx minus omega t. Here a is amplitude or constant, and I is the imaginary part, and x is position dependent, and t is the time dependent function. Now this total wave function, it depends both the time dependent function as well as the phase dependent function. Now we can separate the space dependent as well as the time dependent function, that is total wave function. It is denoted by psi, which is equal to a into e raised to I kx into e raised to minus I omega t. So first function is the phase dependent function, second one with respect to time, that is time dependent function. Now the phase dependent function, I can denote it by wave function psi. So the symbolic, there is a difference, one is capital and another one is small. This is only representation, there is no capital and small usually. So the wave function a into e raised to I kx. So therefore the total wave function psi, which is equal to psi into e minus I omega t. So which accounts wave-like particle, and this wave function which accounts the wave-like particle, and after solving this wave function we will get fundamental equation, and that fundamental equation, it is called as Schrodinger's equation. And these general solutions are dependent on both time as well as the phase variation. And again, there are the two types of Schrodinger's wave equation. One is time dependent Schrodinger's wave equation, another one is time independent Schrodinger's wave equation. So time dependent Schrodinger's wave equation means it depends on both time dependent as well as the phase variation of the function. So here it includes the imaginary part. And time independent Schrodinger's wave equation means it depends only on the phase variation, but that does not dependent on the time. So here it does not contain any imaginary part. Now we have one next derivation, that is time independent Schrodinger's wave equation. We have to derive the time independent Schrodinger's wave equation. So already said, this time independent Schrodinger's wave equation depends only on position and it does not contain any imaginary part. To solve this, I am going to take the de Broglie hypothesis first equation, that is lambda, which is equal to h divided by p, where h is the Planck's constant and p is the momentum. Now if electron is moving in positive x direction, then wave function or the total wave function, it is given by psi, which is equal to a into e raised to I kx minus omega t, equation 2. And also we are separating it by time as well as phase variation, given by the expression 3, that is total wave function psi, which is equal to wave function, that is small psi, into e raised to I minus I omega t, mentioned is the equation 3. Now let us differentiate equation 3 twice with respect to position. So since this psi, that is wave function, it depends on the position, therefore so d square psi divided by t square, which is equal to e raised to minus I omega t, because it is constant, and here this small psi wave function, it depends on the position, means it can be differentiated, that is d square psi divided by dt square, say equation 4. And the same equation 3, now we have to differentiate with respect to time, because earlier we have differentiate with respect to position, now I am going to differentiate it by time. So this e raised to minus I omega t, that depends on time, therefore Now we have the expression that is d square psi divided by dt square, which is equal to minus omega square e raised to I omega t into psi, because psi is the constant. So here I is equal to square root of minus 1, therefore I square equal to minus 1. So equation 5. Now I can consider the travelling wave equation. This is very important step. I can consider it by directly. So the travelling wave equation, generally it is represented by d square y divided by dx square, which is equal to 1 divided by v square into d square y divided by dt square. So here y is nothing but it is the displacement of wave, and here both position as well as time dependent function, that is x is position and t is the time and v is the velocity. So in wave function or wave motion is also it is represented by psi. In previous case displacement equation it is denoted by y, but in case of electron motion it is denoted by psi. Therefore the same analogy I can use, and the equation I can write in terms of psi, that is d square psi divided by dx square, which is equal to 1 divided by v square into d square psi divided by dt square. Say equation 6. Now we have to substitute equation 4, equation 5 in equation 6, because already we have determined d square psi divided by dx square and d square psi divided by dt square, that is differentiate twice with respect to position as well as time. Now you can substitute this and you will get final equation as d square psi divided by dx square, which is equal to minus omega square divided by v square into psi. If lambda and mu are both wavelength and frequency, then omega, which is given by 2 phi mu, and velocity it is given by frequency times lambda. Now we can substitute this and we'll get d square psi divided by dx square as minus 4 phi square divided by lambda square into psi. Now this expression we have convert, or we have to take in terms of 1 by lambda square, or 1 by lambda square will get as minus 1 divided by 4 phi square into psi into d square psi divided by dx square. Say equation 7. Now this particle having mass m and moving with the velocity v, then kinetic energy expression we can give in terms of 1 by 2 mv square. And also we know that in terms of momentum, so this kinetic energy it is given by p square divided by 2m. Equation 8. Now as we know that from equation 1 or de Broglie hypothesis, that is lambda which is equal to h divided by p, or p which is equal to h divided by lambda. So p which is equal to h divided by lambda, the same expression we have to substitute in equation 8. We'll get kinetic energy which is equal to h square divided by 2m into 1 divided by lambda square. And also we know that 1 by lambda square value in equation 7. So substitute this and you will get equation 10, that is kinetic energy which is equal to minus h square divided by 8 phi square m into 1 by psi into d square psi divided by dx square. Now this electron is very fast moving, and since it changes its field, therefore it exhibits some potential energy. Therefore the total energy it is nothing but it is the sum of kinetic energy as well as potential energy. Kinetic energy already we have found, and potential energy I can represent it by capital V. Therefore the total energy which is equal to minus h square divided by 8 phi square m into 1 by psi into d square psi divided by dx square plus potential energy as V. Now rearrange the expression and you will get d square psi divided by dx square which is equal to minus 8 phi square m divided by h square into e minus v of psi, and also after rearranging you will get the final expression, that is d square psi divided by dx square plus 8 phi square m divided by h square into e minus v of psi, which is equal to 0. So this is the time independent Schrodinger's wave equation.